Now that we have introduced you to the Necrosis brothers, let's take a look at their pictures. Classically, liquefactive necrosis, almost always referring to the brain, results in increased fluid, mostly because if you think of the histology of the brain, once you damage that type of tissue, there's really nothing in there, no type of collagenous framework to make it firm, like in other organs. So any nonspecific injury to the brain will result in, among other things, edema, increased water, increased H2O, increased protons, increased MRI signals. That's one way of looking at it. Here is some bilateral frontal lobe injury resulting in fluid and therefore increased signals. Here's caseous necrosis. It's a lung. It has tuberculosis. If you cut through that lung with a regular knife, it might have a cheesy consistency, and that's why it's called caseous necrosis. However, caseating granulomas are often applied as a microscopic term as well. Here is a blood vessel that has a finely hyaline pinkish granularity to its wall, which has the H&E characteristics of fibrin, but many other things do too. So this is called fibrinoid necrosis. And when you hear fibrinoid necrosis, you think it's probably going to be in a blood vessel. Here is gangrene, and it's in the early stages of gangrene where there still is a lot of increased fluid reacting to it. So it's called wet gangrene, and it's called wet because it's wet. Later on, when the fluid is absorbed, it's called dry gangrene. And in most cases, gangrene is an ischemic type of necrosis due to lack of blood flow. Uh, we talked about ischemic or hypoxic injuries. There's also a type of injury called a reperfusion injury, where tissue is technically dead or dying or whatever, perhaps in that la la land area, and you reintroduce blood flow into it. That in itself could be damaging because when you do, uh, you are now introducing things which activate the dead tissue and cause it to have further damage. You can also have a chemical type of injury, and a chemical injury can be direct by virtue of it being toxic, or it could be indirect if the chemical is converted into a toxic metabolite. So, an ischemic injury, as you might have guessed, uh, it could be reversible, but once it's at the point where there is cell death, that's irreversible. And dead tissue, due to irreversible ischemic changes, is called an infarct. In ischemic reperfusion injury, the restored blood flow reintroduces oxygen within cells, which could cause free radicals. It could damage proteins, DNA, and plasma membrane. As a matter of fact, what I just rattled off is the exact Wikipedia definition of reperfusion injury. And I am a great, great, great believer in Wikipedia, and I hope you always have your wiki on your laptops with Wi-Fi while you're listening to lectures in school. Chemical injury could be a toxic type of effect due to toxic chemicals. It could be due to drugs, common over-the-counter drugs such as Tylenol. Of course, there's always a dose relationship, and chemical injury could cause increase in free radicals within the cell, organelle changes or disruptions or death, as well as direct DNA damage. How do you like that for a pharmacology lecture in 30 seconds or less? Let's talk about apoptosis now. We already defined it as pre-programmed normal cell replacement, and we said it was different from pathologic death, which is associated with all the previous things we talked about which cause necrosis. Apoptosis comes from the Greek word which means falling off. So normally, when you have cells in embryos which have to go away for the embryo to differentiate, to grow, to become something else, that's a normal apoptosis process. You see a endocrine gland that is much smaller than it should be because it lost cells, perhaps due to aging, that's also a normal apoptosis. When you see that the growth centers of epithelial surfaces, such as crypts within the GI system, have a high turnover and a high replacement, that's also a normal apoptosis. When you see inflammatory cells, lymphocytes, neutrophils, macrophages in an area, and it is eventually resolved or cleaned up, those cells have gone bye-bye by virtue of apoptosis as well. Sometimes harmful cells can apoptose, and that's a good thing, and it's a normal body thing. If you have a cell that shouldn't be there, often, I guess you could compare this to an embryo that is irreversibly damaged. It's just never allowed to grow up. A lot of times T cells, which are cytotoxic, are involved in the cleaning up process as well. I'm not going to go into the chemistry because I hate chemistry. There is also a type of apoptosis called pathologic apoptosis. And in pathologic apoptosis, it's not a pure normal replacement. Sometimes it's associated with pathologic processes such as obstruction of a duct, tumor cells, and toxic effects of cells like chemicals and pathogens. This shows you that there is a spectrum between pure replacement of cells called apoptosis and death of cells due to pathogens and other things. So remember, apoptosis necrosis is a spectrum. In apoptosis, there's a decrease in cell size or shrinkage. There's an increase in chromatin concentration, or what we call hyperchromasia. The cell then becomes smaller or pycnotic. It then dissolves and breaks up by a spectrum called karyorrhexis, or fragmentation of the nucleus, to karyolysis, which is dissolving of the nucleus. Often you see an increase in membrane blebs as well, and the end result of all apoptosis is that the cell will then be phagocytized. Here's a normal cell up here, and here's a cell undergoing apoptosis. You can see hyperchromasia, you can see nuclear fragmentation or karyorrhexis, and you can start to see dissolution of the nucleus or karyolysis. So we see pygnosis, hyperchromasia, karyorrhexis, karyolysis, 4 new words to learn. Eventually, it will result in phagocytosis by cells which are capable of phagocytosis, generally known as macrophages, in which substances are then completely engulfed. And here, you know that the substances in this macrophage is red blood cells, because you can still see that they look similar to the ones that haven't been phagocytized. We'll get into that in the next chapter. Let's talk a little bit about the biochemistry of apoptosis without actually going into all those crazy equations. Let's just say there's a family of enzymes resulting in the digestion of various intracellular proteins called caspases, which are triggered off by a very complex mechanism. There's also breakdown of the nucleic acids within the cell as well, and at some point the chemistry is then recognized by phagocytes, chiefly macrophages, which will result in the phagocytosis and digestion of that apoptotic cell. Let's end here because I said we only have 10 seconds left, and we'll start out with subcellular responses to injury on the next one. Bye-bye.